Welcome back to the deep dive. Today, we are going to look at something that is happening quietly, almost, invisibly in the background of the current AI explosion.
Mhm.
And I have to be honest, when I first looked at the stack of papers you brought in, I thought I'd walked into the wrong recording booth.
Because there were no chatbots writing sonnets or generating images of cats in spacesuits.
Exactly. Everyone is talking of the flashy stuff right now.
Yeah.
You've got deep fakes, you've got AI Elvis singing Baby Got Back.
Right.
It's all very pop culture, it's very
Yeah.
visible. But the research we're covering today, this feels different. This isn't about generating a funny image.
Right.
This looks like heavy duty industrial strength engineering.
It is. But that's actually why it's so exciting. We're looking at a massive collision between two worlds that usually, well, they don't talk to each other nearly enough.
Okay.
On one side, you have the world of scientific computing, the serious math used to simulate jet engines, heat shields for spacecraft, things like that. And on the other side, you have the modern AI revolution.
And the problem, as I understand it from reading through this, is that these two worlds historically speak completely different languages.
They do.
It's almost like a square peg round hole situation.
That's the perfect way to visualize it. It comes down to structure.
Structure.
Yeah. Think about standard machine learning, the stuff that powers facial recognition or your photo app. It craves order. It wants a perfect grid of pixels or a fixed list of numbers. It wants a checkerboard.
Right, because a photo is just a grid of pixels, height, width, color.
Yeah.
Very organized.
Precisely. But the real world isn't a checkerboard. If you're simulating a metal plate that's been twisted in a car crash, or the airflow over a curved turbine blade, you can't use a perfect grid.
Right.
You use what engineers call an unstructured mesh.
Unstructured mesh, that sounds messy.
It is messy. You have triangles and tetrahedrons everywhere. Big ones where nothing is happening, tiny ones where the stress is high, weirdly connected shapes. It's a geometric jumble.
So standard AI looks at that mess and says, I quit. I can't process this.
Essentially, yes. A standard neural network breaks because the input size keeps changing. But today, we're talking about the solution to that disconnect. We're diving into graph neural networks.
GNNs.
For
GNNs, yeah.
Okay, let's unpack this, because when I hear graph neural network, I immediately think of like pie charts and bar graphs, maybe a boring PowerPoint presentation.
Right.
But that's not what we're talking about here, is it?
Not at all. In mathematics and computer science, a graph isn't a chart. It's just a way of saying a bunch of things connected to each other.
Oh, okay.
You have dots, which we call vertices or nodes, and you have lines connecting them, which we call edges.
Simple enough. So a social network is a graph.
Exactly. That's the classic example. You are a node, I am a node.
And if we are friends, there is a line and edge connecting us.
That's it.
The papers use a really good analogy to explain how a GNN actually processes information on this graph. The viral example.
Mhm.
I found this really helpful for visualizing the mechanics because it takes the abstract math and, makes it human. It's the best way to get the intuition before we get to the physics. So imagine a community. The people are the nodes.
Okay.
And their interactions, talking, shaking hands, sharing a meal, are the edges connecting them. Now, suppose we want to predict who is going to get infected with a virus.
Right. And here's where the structure problem usually kicks in for standard AI. In a traditional neural network, you need a fixed number of inputs, like filling out a form with 10 boxes.
Exactly. But in a social network, everyone is different. You might be a social butterfly connected to 50 people. I might be a hermit connected to 2.
No comment on who is who in this scenario.
We'll leave that to the listeners. But think about the math. A standard neural network, specifically something called a multi-layer perceptron or MLP,
Right.
it expects every single person to have the exact same number of friends. It expects a rigid column of data. If I feed it your 50 friends and then my 2 friends, the math just falls apart.
So how does the graph neural network handle the popular kid and the hermit at the same time?
It uses a concept called an aggregation function. This is the GNN superpower.
The superpower, okay.
It allows the network to look at a node, say UN, and gather information from all your connections, whether it's 2 people or 2,000.
And it summarizes that info.
Precisely.
Yeah.
It typically uses simple order-independent operations like summation or maximum.
So it adds it all up.
It sums up the viral load from all your friends or finds the friend with the maximum risk. That operation produces a single fixed-size summary that a standard neural network can finally handle.
So it creates a bottleneck, but a smart one. It takes the messiness of the crowd and boils it down to here is the total pressure on this person.
That's it. And the sources break this down into a specific three-step rhythm, often called the message passing layer.
Okay.
And understanding this rhythm is key to understanding how we simulate jet engines later.
All right, I have the rhythm right here in my notes.
Yeah.
Step 1 is the edge update.
Think of that as the interaction itself. Two people meet, something happens, a virus is transmitted, maybe a rumor is whispered.
An exchange of data.
An exchange of data along the connection.
Step 2, aggregation.
That's the gathering phase we just talked about. The person collects all those messages from every interaction they had that cycle.
Okay, I talked to 5 people, 3 were sick, 2 were healthy.
Exactly.
And step 3, vertex update.
The person updates their own status. Based on all these interactions, am I now infected? Am I cured? And then the cycle repeats.
It effectively lets the AI slide over the network, treating everyone individually based on their specific connections, rather than trying to force everyone into a rigid box.
And that flexibility is exactly why it works for engineering. Because a mesh on a jet engine is just a social network of physical points pulling and pushing on each other.
Which brings us to the Rosetta Stone moment of this deep dive. This was the part of the research that made me stop and reread.
Right.
You're saying that the matrices used in physics simulations are actually just graphs in disguise.
They aren't even in disguise, they are graphs. This is the big realization. In scientific computing, we use these massive, sparse matrices. Now, a matrix is just a giant grid of numbers, but sparse means almost all the numbers are zero.
Why are they zero? I mean, usually when I think of data, I think of full spreadsheets.
Think about a metal plate. If I heat up a specific point on the bottom left corner with a blowtorch, it doesn't instantly heat up a point on the top right corner.
Yeah.
It only affects the points right next to it.
The relationship is local.
Exactly. So in the matrix that describes that plate, there is no connection, no number between distant points. It's a zero. So if you draw a line between every point that actually interacts,
You get a graph.
you get a graph.
Yeah.
The matrix describes the topology, who is connected to whom.
And the numbers in the matrix, the non-zero ones.
Those are just the weights on the edges. If point A pushes on point B really hard, the edge weight is high. If they barely touch, it's low.
So when engineers do that classic operation matrix vector multiplication,
Yeah.
which I know is the bread and butter of all these simulations,
It is exactly identical to one layer of a GNN.
that is wild. You're saying we've been doing GNNs since before AI was even a thing.
In a way, yes. When you multiply a sparse matrix by a vector, physically, what are you doing? For each point, you look at its neighbors, you multiply their values by the connection strength,
You sum them up.
you sum them up, and you update the point.
That is exactly the edge update, aggregation, and vertex update we just talked about with the virus.
It's a one-to-one mapping. Physics simulation is message passing.
So we have this dictionary now. A matrix is a graph. Multiplication is a GNN layer. The papers even list other algorithms that map over perfectly.
Oh, the list goes on. Things like weighted Jacobi iteration, which is a method for smoothing out errors in a system, or the power method for finding eigenvalues, even complex stuff like algebraic multigrid. It all translates.
Okay, but here's where I have to play devil's advocate, and I think the listener might be wondering this too. If we already have these algorithms that work perfectly well, and they map directly to GNNs,
Yeah.
why do we need the AI?
Right.
Are we just rebranding math to make it sound cool?
That is the pivotal question. If we just use the GNN to mimic the math we already have, we haven't gained much. Maybe a new notation. But the goal isn't just representation,
It's improvement.
it's improvement.
How do you improve on math? Isn't math distinct? Like 2 plus 2 is 4.
The rules of arithmetic are fixed, yes. But the strategies we use to solve massive problems are often based on heuristics, essentially educated guesses.
Guesses. In building a jet engine, that's comforting to know next time I'm on a flight.
Well, rules of thumb might be fairer. We know they work generally, but they aren't perfect for every single spot.
Okay.
Take the Jacobi method we mentioned. It's an iterative solver. It tries to smooth out errors in the calculation over and over. But to make it work, you need a relaxation weight.
A number you multiply by.
Right, a number you multiply the error by to dampen it.
And how do engineers pick that number?
Usually,
Yeah.
they pick a standard number like 2/3. It's the industry standard. Or they calculate a classical optimal number based on some global average of the matrix.
But these are rigid, one-size-fits-all rules.
Exactly. It's like saying every person in the social network should take the exact same amount of medicine, regardless of how sick they are.
And the GNN changes that.
The paradigm shift here is that we replace those fixed rules with small, trainable neural networks, little MLPs embedded right inside the algorithm.
So instead of humans saying always multiply by 2/3,
The GNN looks at the local geometry of the mesh and says, wait, this part is weird. It's twisted. I'm going to use a different weight right here.
it stops following a rigid rule and starts learning the topology.
Exactly. It's not just running the algorithm, it's optimizing it in real time based on the data. It creates a custom tailored strategy.
Let's look at the case study from the source material because this really proves your point. They ran an experiment with a heat map, right?
Yes, a 2D Poisson operator, which basically models how heat diffuses across a surface. But they made it tricky. They used a square mesh, but they introduced a skinny band.
A skinny band.
Imagine tiling a floor with perfect square tiles, but then you have one strip where the tiles are squashed tall and super thin. That's called anisotropy.
Ah,
It creates a sort of bottleneck or fast lane for the math that confuses standard solvers.
so the standard multiply by 2/3 rule usually fails there.
It struggles. It doesn't dampen the error efficiently because the geometry isn't uniform. The error just bounces back and forth in that skinny channel.
So what do they do?
So the researchers trained a GNN to learn its own diagonal relaxation matrix, basically asking the AI, you tell us what the weights should be at every single point.
And the results were pretty stark.
They were. The GNN outperformed the standard weights in 100% of the test cases. But more impressively, it outperformed the classical optimal method.
The mathematically best static guess.
Right. It beat that in over 75% of cases.
Why? What did the AI figure out that the mathematicians missed?
When they visualized the weights the GNN shows, they saw something fascinating. The GNN didn't choose a smooth, constant number. It assigned huge values to the boundaries of the mesh, to the corners, and specifically to that weird, skinny, anisotropic band.
So it recognized the trouble spots.
It intuitively felt the geometry. It learned a spatially varying strategy. It realized, hey, heat flows differently in this skinny strip, so I need to push harder here to smooth out the error.
Something a simple constant weight could never do.
Never, because it treats every point the same.
That's incredible. It's almost like the AI has a better intuition for the physics than the static formula does.
It's not that it knows physics better, but it can adapt to the geometry of the physics better. It sees the bumps in the road and adjusts the suspension.
Whereas the classical method just has stiff shocks.
Exactly.
There was another case study that went the opposite direction, right? Instead of helping the solver, it was about figuring out the hidden physics.
Right, the diffusion coefficients study. Usually in simulation, you start with the physics, say the diffusion rates of a material, and you build a matrix to simulate it.
Forward engineering.
Forward engineering. And here, they tried to go backward. They gave the GNN the matrix and said, tell us what the underlying physics were.
What were the diffusion coefficients?
Exactly. And this is incredibly hard because of that same messiness. If you have diffusion that is strong in one direction but weak in another, again, that anisotropy, it's very hard to disentangle that.
And the GNN.
It nailed it. It successfully predicted the coefficients. But the kicker, the part that really matters, is that it worked even when they tested it on frequencies it had never seen during training.
It extrapolated. That's a big deal in AI.
Yeah.
Usually AI fails when you take it out of its comfort zone.
Precisely. That suggests it didn't just memorize the answers, it actually learned the relationship between the matrix structure and the physical parameters.
And the application for this.
Yeah.
Why do we want to work backward?
It connects to something called algebraic multigrid, or AMG. It's one of the most powerful solvers we have, but it relies on a step called coarsening.
Coarsening.
You have to take a fine mesh, millions of points, and simplify it to a coarse mesh, thousands of points, to solve it quickly.
Like zooming out to get the big picture.
Exactly. But to zoom out correctly, you need to know which connections are strong and which are weak.
Okay.
If you cut a strong connection or group the wrong nodes together, the whole solver stalls.
And standard formulas struggle with that decision.
When the mesh is weird or stretched, they often guess wrong. The GNN, because it can infer those diffusion coefficients accurately, can correctly identify the strong and weak connections where the formulas fail.
So it acts as a guide. It tells the massive solver, hey, don't cut that wire, it's important.
Precisely. It makes the zoom out process much more robust, which speeds up the whole simulation.
This sounds revolutionary, but I want to pump the brakes for a second. We have a section in the notes here called reality check.
Mm.
If GNNs are so good at linear algebra, Should we just throw out all our old libraries? Should we delete Trilinos and PTSC and just run everything on GNNs?
A hard, emphatic no. And the source material is very clear on this. GNs are not here to replace the heavy lifters.
Why not? If they were smarter, why aren't they better?
Because they are slow.
A classic trade-off.
In raw computational efficiency, a GNN is significantly slower than a specialized library like PC.
They-
Those libraries are written in C++ and Fortran. They have been optimized for decades.
Right.
A GNN adds a massive layer of overhead. You're running a neural network for every single point.
So you wouldn't use a GNN to actually do the multiplication in a production run?
No, that would be like using a team of philosophers to dig a ditch. They might have a great theory about the best way to dig, but if you have 1,000 miles to cover, you just want a bulldozer.
That is a great analogy. So where is the sweet spot?
The sweet spot is synergy. You use the GNN as the brain and the classical solver as the brawn.
Okay, explain that workflow.
You let the GNN run once or occasionally. It looks at the problem, analyzes the weird geometry, and says, okay, for this specific mesh, you should use these relaxation weights.
It sets the strategy.
It sets the parameters. Then you hand those optimized parameters to Trilinos or PTC, the brawn, and let them do the heavy number crunching at full speed.
So the GNN provides the map, and the classical solver drives the car.
Exactly. And honestly, that's a more realistic future for AI and science. It's not replacing the math, it's wrapping around it.
Good.
The paper also points out you shouldn't use GNNs if you have structured data.
Right. Don't use a hammer if you need a screwdriver.
Exactly. If you are working with images, use a CNN. If you have fixed vectors, use an MLP. Don't overcomplicate it. GNNs are specifically for the unstructured, messy problems.
That distinction is really helpful. It's not a magic wand for everything. It's a specific tool for messy geometry.
Right. And training them is resource intensive. It's not a free lunch. But for these high value engineering problems like designing a fusion reactor, that upfront cost of training the brain is worth it if it makes the brawn run 50% faster later on.
So, bringing this all back to the big picture, we started with AI Elvis and deepfakes. But what we found here is something arguably more profound.
I think so. We are seeing AI move from just mimicking human outputs like art or text to understanding the fundamental language of the physical world.
We've moved from AI Elvis to AI solvers.
That's a good way to put it.
Mm.
GNNs are effectively acting as a bridge. They allow machine learning to cross over into the messy, unstructured reality of scientific engineering.
And what sticks with me is that visual of the heat map. The fact that the AI learned to put more weight on the corners and the skinny band. It raises a really provocative thought to leave on.
What's that?
We typically think of learning in AI as acquiring facts, learning what a cat looks like or what the capital of France is. But in this context, the GNN is learning strategy.
Yes.
It's finding numerical shortcuts in the geometry that human mathematicians might have missed or couldn't easily codify.
Right. We have our rigid formulas and we think they are the law. We think the math is settled.
But if an AI can intuitively feel where a mesh is weak or strong and adjust the math accordingly, it makes you wonder, what other rigid mathematical rules in our textbooks are actually just flexible guidelines waiting to be optimized?
That is a fascinating thought. Are we solving math problems or are we negotiating with them?
Exactly. We will leave you with that to chew on. Thanks for listening to this deep dive into the intersection of AI and linear algebra. We'll see you next time.